Okay, here we are back again. This is three-phase motors part 3. So we just finished on slip speed at the end of the last video. Remember, our slip speed is the difference between the theoretical full speed of my motor, which is my synchronous speed, and the actual full speed of my motor. So the next thing is the speed and torque characteristic graph. This is our graph here. You'll need to have a look at that and get to grips with each of these labels here. The performance of the three-phase squirrel cage induction motor can perhaps be best portrayed by the use of a speed torque graph. Such characteristics as starting torque, running torque, full load running speed, and others can be evaluated and compared easily using this method. The figure shows a typical graph. The load line in this case represents a load whose torque increases only slightly between zero speed and running speed. So what have we got here? So on the vertical axis we have our torque, that's how much force the motor is producing, and on the horizontal axis we have speed, that's how faster the motor is running. So here we have our starting torque, so that's how much torque I produce at the start. Obviously if we have a high starting torque, then that line will start up here somewhere. If we have a low starting torque, it's going to be down here somewhere. Torque, as we can see here, is gradually increasing as our speed increases. And it says there, the load and line in this case represents a load whose torque increases only slightly between 0 and running speed. So if we had a large increase in torque, it would be up here. This is our pull-out torque. So pull-out torque is the maximum torque that we can produce. Beyond that point, if we're asking the motor to produce more force than that, it will stop. This is the maximum force that it can produce. Once we're putting so much load that it can no longer produce any more force, then obviously the speed is going to reduce quickly. That would be stalling. We have as then beyond that peak torque, then our torque is going to fall quite quickly as we try and increase the speed. So we're increasing the speed from here up to about here, right? So only a small increase in speed there to there. So that's our 2 points there. So our torque will fall away dramatically. Our torque will fall away dramatically at that speed. That's our normal speed, so that's just our like running no load speed, and there's our running torque there, so that's how much torque is produced at normal speed essentially, and our load torque is represented by that line there. There's 3 important points on the curve that you need to recognize. Starting torque, this is the maximum torque the motor can produce when starting. So if our pull-out torque is important, right? Because if we exceed our pull-out torque, then the motor will cause us significant problems. In theory, the motor will stall. But we also need to be aware of that starting torque, because as our torque ramps up across the speed curve, it's no good to have a load that will be under our pull-out torque. If it's over our starting torque, we need to have more torque than we need, or at least the same amount of torque as we need to move the load at all points along that graph. Pull-out torque is the maximum torque that the motor can produce. If the load torque exceeds the pull-out torque, the motor will stall. Running torque, at this point, the driving torque equals the load torque. So the force generated by the motor is equal to the force required by the load. Its position on the curve is so chosen that the motor can stand a big overload without stalling. So even if, so that's our, what was it there? Running torque. Running torque was here. So we've got a lot of room. We've got a lot of headroom there. So if we get a big overload, we're not going to destroy the motor instantaneously. If our running torque was way up here by our pull-out torque, then that would mean any small change in the load, any additional load for whatever reason, a fault or something, is going to immediately drive that motor past its pull-out point. The load torque line indicates the type of load being driven by the motor. It will vary according to the characteristics of that load. To help your understanding of how the speed torque graph should be read, study the examples given below and see how the characteristics of two different loads placed on a squirrel cage induction motor can be read from the graphs in the following figures. Number one. So where are the graphs that go with this? Okay, I don't know. Let's carry on. So number one, normal full load. At startup, the motor produces the torque speed graphed in figure A. Because the motor torque exceeds the load torque, the motor accelerates. The speed rises until the motor torque equals the load torque, then the speed will stabilize. Okay, so that's normal. This is a normal situation. As I said, we need to be able to produce more torque at startup than the load requires. So it's not just about having more torque at normal running speed. We need we need more torque. We need to be able to produce more torque in the motor than the load requires at all speeds, particularly at startup. Because the motor torque is higher than the load torque at startup, then the motor will start to speed up, and it will keep speeding up until the motor torque equals the load torque. Remembering, of course, that the torque will slowly will start to decrease. Beyond a certain point, the torque will start to decrease as the speed increases, because remember, if our speed hits the synchronous speed, then there'll be zero torque effectively. So as the motor speeds up, then the torque will drop, and then once the torque produced is equal to the load required, or the torque required by the load, then the speed will stabilize. It will stay the same. Second example is a stalled motor. The motor does not start because the load torque is greater than the driving torque at starting. If the motor could be run up to a point of speed corresponding to the intersection of the two curves and then be coupled to the load, it would accelerate the load. Its final operating point is, however, too close to the pull-out torque of the motor. Very little overload will cause the motor to stall. Okay, so hopefully we have a graph of this further on in the slideshow, but if we don't, then the explanation here is that if the load torque is higher than the starting torque of the motor, then the motor won't start. But if we ran the motor up at no load, so it was running at full speed, and then say engaged the clutch to bring the load in, I talked about that earlier in previous video about clutches and just some sort of mechanical method of reducing the loading on the motor at startup. So then we close the clutch, then it's going to be okay, it's going to run that. But if we're right close to that maximum torque of the motor, then a very small overload will cause big problems with that motor. Okay, effective rotor resistance on torque. The introduction of resistance into the rotor circuit of an induction motor produces three effects. The rotor current is reduced, resulting in less stator current. The starting torque is increased because the rotor and stator magnetic fields are more in phase with each other. And the slip speed is increased. Slip speed being the difference between theoretical full speed and actual speed. So for reduced current starting, we want to add resistance, but to increase the running speed, that means we're increasing the running speed gives us less slip. Then we want to remove the resistance. For this reason, an external resistance is added in the circuit of a wound rotor and gradually reduced as the motor speed builds up. And we talked about that earlier, adding in resistance into the rotor windings, external resistors in the rotor windings. With the resistance completely removed, the wound rotor behaves like a cage rotor, so it just be the same as a cage motor. The torque speed characteristics of a typical three-stage wound rotor motor is shown in the following slide. And then we have it there. When all the resistance is in the rotor circuit, the starting current is low and the starting torque is high, as shown by curve A. It's this guy here, the solid thin black line. So we have speed here again and torque here. So at zero speed we have pretty high torque, and then as the speed increases the torque drops away pretty smoothly. If the resistance is left in, the full load torque would occur at about 25% slip, which means the motor would be running at 75% of full speed. that's there. So that's our torque there. So once the motor hits that rated torque, it's not going. It's going to stop, right? Once our produced torque equals our load torque, then the motor won't stop, but it will stop accelerating. So it'll stop at that speed. So we'll only get this much speed, which is there's 75% of speed. As one stage of rotor resistance is shorted out and the operating characteristics change to curve B, and then again for curve C. So we can remove some of the resistors, and that will give us curve B, which is the thick dotted line here. Again, for curve B, we'll get, if we just ran it with all those resistors in, then we'll get more speed than we got out of the first one, but still not full speed, not our ultimate speed. And then C, again, we've taken some of the resistance out, but we've left some of the resistance. C, I think we've taken all of the resistance out. So then we have the similar curve to what we had on that previous slide with the curve on that one. So torque increases to a point, and then it will start to, that's our pull-out torque, and then this torque is going to drop off as our speed increases past that point until we get to pretty much rated speed, so we've got no resistance there. Normal starting procedure is to start the motor with all the resistance in the rotor circuit and then gradually reduce it as the motor speeds up. The motor characteristics for this procedure is shown by the thicker curve D. So then we get, if you look at curve D there, then we're getting the best parts of all of those. So on the first part we get the curve A, and then when curve B takes over we take out that resistance, and then when curve C comes high we take out that resistance as well. So we get a torque curve along that line D, which is obviously better at slower speeds than line C, but gives us a higher full speed than line A or B. Double cage rotor motors. The double cage rotor, or Boucherot, I don't know, has a similar effect as the wound rotor in that it has a double row of rotor bars forming two separate cage windings. The double cage motors can be started the same way as the normal squirrel cage induction motor. The outer cage has the greater resistance. Okay, here we are back again. This is three-phase motors part 3. So we've just finished on slip speed at the end of the last video.